All right. Hi, good afternoon. Let's get started. So the you should have received your the instruction to access your exam 4. So if you just go to your Canvas page, click on the exam 4, and you should be able to see the grade as well as a PDF file with all the marks on the exam. If there's any questions from the exam, feel free to email me and Professor Gibson to clarify any confusions. But if you want some parts to be regraded, I think you have to email Professor Gibson with a little bit explanation like before. Any questions about the exam before we move on to something that we didn't finish last time? All right. If you don't have questions, so I'm going to begin. I'll try to do 2 examples today. I want to begin with the first example, which is on eigenvalues and eigenvectors of a 3x3 matrix. And after that, we're going to use eigenvalues to solve a system of linear ODEs. Professor Gibson already did some work on that, so we're going to, kind of practice that concept. If you have any questions, feel free to unmute yourself or put it in the chat box. Okay, here we go. Yeah, no problem. So the last homework problem. Okay, go ahead, Justin. What's the question? Is this like the most recent homework that's due, I think, this Sunday?
Yeah, it's the most recent one where it's the initial value problem.
Okay. Let's see. If you give me a minute, let me pull out the homework, okay? I can see what it is. Yeah. Hold on. Let me. Okay, so it's still recording. Dashboard. So it's homework 7. All right, is our last problem. Excellent. Okay, that's a good question. So I'm actually going to show you with the second example I have, like how do you actually use the initial conditions to in that part of solving the system. Is that okay?
Sounds good. Thanks.
Yep, that's a good question. I'll definitely cover that. So let me share my screen again. All right, can you see the notebook that I'm using? Anyone, please let me know. Okay, great. So make sure it's a recording. Good. All right, so the first example I want to talk about is finding eigenvalues and eigenvectors of 3x3 matrix. So we have seen examples of 2x2 matrix, but I do want to go through a 3x3 matrix. It's just that a lot of times we work with example more than just 2-dimensional. So the example is A equals 2, 0, 0, 0, 0, 4, 5, 4, 3. And then we want to find the eigenvalue and eigenvector. The process is the same. So the first step, well, before I do that, let me write down a few important formulas we might use. The first one is A times eigenvector V equals lambda times V. We might use that, but we might use a factor form, which is A minus lambda I times V equals 0. Actually, more often we use this one rather than the one above to find the eigenvector. And then the next one is that if we want a non-zero eigenvector, we must have determinant, so det of a minus lambda I equals 0 for non-zero eigenvector. And this is also going to allow us to find eigenvalues, which we're going to find first. So mostly we're going to use those two formulas as highlighted. So let's first find eigenvalue. So step one, we need to find a minus lambda I, and that's going to be 200045043 minus lambda times identity. So a is 3 by 3, so identity has to be the same dimension. So that's a 1, 1, 1 on the diagonal and 0 everywhere. This is a 3 by 3 identity matrix. And if we distribute lambda into the identity and then subtract it from A, we should end up with 2 minus lambda, 0, 0, 0, 4 minus lambda, 5, 0, 4, 3 minus lambda. So if you remember, I kind of mentioned this. If you want to avoid some work, take the shortcut. So you basically subtract lambda from all the diagonal entries of A. So that will be a minus lambda I. You can use that directly in the future. And then the second step is find the determinant of a minus lambda I. That, because it's a 3 by 3, so I'm going to use what I did last time by setting up the augmented matrix. So that's going to be 2 minus lambda 0, 0, the given matrix. Well, not the given, the a minus lambda I. 4 minus lambda 5, 0, 4, 3 minus lambda. But I'm going to augment this with the first two columns. So 2 minus lambda 0, 0, 0, 4 minus lambda 4. That's a vertical line, means determinant. And from here, we can just draw backslashes and the forward slashes to figure out the determinant. So backward slashes, that's 1. This is the second one, that's the next one. So let me do one at a time. So this is going to be 2 minus lambda times 4 minus lambda times 3 minus lambda. And then the next one will give me 0 times 5 times 0. So I'm adding them together. So that's going to be plus of 0. I'm not even going to write it. And then the next one also going to be plus of 0, right? Because we got 2 zeros there. So that's all I have from backward slashes. And then we need to subtract forward slashes. So that's the first one. It's going to be 0. This is the next one. It's non-zero. So that's going to be minus 2 minus lambda times 5 times 4. And then the following forward slash also going to give us a 0. So I'm not going to write it. So that's all I have as expressions in the determinant. Okay, so we can set it equal to 0, but here's a trick we can use. So instead of directly expanding all the terms set it equal to 0, what we're going to try to do here is we're going to try to find the factored form from here, from the very beginning, if possible. And then we're going to set it equal to 0 at the very end. It's going to save a lot of work to find lambda. So is there anything I can factor? I'm going to factor first. So it looks like I have 2 minus lambda and a 2 minus lambda from both parts. So that's a factor, 2 minus lambda. The remaining, I'm going to put it together. So that's a 4 minus lambda times 3 minus lambda minus 5 times 4, 20. Now, what I factored out, so I'm not going to touch it, just leave it. But what about the bracket term? Is there anything I can factor? Not really. In that case, we're just going to expand it and then maybe try to factor towards the end. So that's going to be 3 times 4, 12 minus 3 lambda minus 4 lambda plus lambda squared minus 20. I'm going to do a little bit quick here. Hopefully that's okay. So that's just going to give us lambda squared minus 7 lambda plus minus 8. After I simplify, which I can factor the part in the brackets. So that's going to be 2 minus lambda minus 8, lambda plus 1. And I don't even have to keep the bracket sign with it. I can drop it. So that's the completely factored form. That's good, because at this point, if I set it equal to 0, I should have something really nice for lambda values. So from here, so step 3, we're going to set determinant a minus lambda I equals 0. So that means this part is going to be equal to 0. So 2 minus lambda minus 8, lambda plus 1 equals 0. So therefore we have lambda equals 2. I'm going to call that lambda 1. Lambda equals 8. I'm going to call that lambda 2. And then lambda equals -1. That's lambda 3. So those are the eigenvalues. Any questions about finding eigenvalues at this point? So after we find eigenvalues, I'm going to find eigenvectors. To find eigenvectors, I'm going to use the a minus lambda I times v equals 0, the part I highlighted in pink there. So I'm going to use that formula to find eigenvector. But note that in this formula, there's an a minus lambda I, right? That's a matrix. And I already have that. I found that earlier when I don't know what lambda is, I just use lambda. So that's the matrix we're going to use. And I'm just going to plug in lambda value into that matrix and then use it instead of like finding a minus lambda I from scratch. So keep that in mind. So to find eigenvector, we're going to use a minus lambda I times v equals 0. And the v we can just see is going to be x, y, z, because we have a 3 by 3 matrix to begin with. And the a minus lambda I is the part that I circled in green. So if I know, for example, lambda 1 equals 2, so I'm going to put 2 in there. So for lambda 1 equals 2, I can figure out a minus lambda I by using that matrix, which is 2 minus lambda, 2 minus 2, 0, 0, 0, 4 minus lambda, 4 minus 2, 5, and then 0, 4, 3 minus lambda, 3 minus 2. So I'm going to take the lambda, replace it with 2. And then I can just figure out the value from here. So that's a 0, 0, 0, 0, 0, 2, 5, 4, 1. So that's a a minus lambda I. It's very quick to find it. Just substitute lambda with a 2 there. And from here, I'm going to use the formula above. So a minus lambda I times v equals 0. So put in the matrix form. So that's a 0, 0, 0, 0, 2, 5, 0, 4, 1 times x, y, z. That should equal to 0, 0, 0. Then we can convert this into system of equations. There's other ways to find x, y, z. But for now, I think it's easier if we just use system of equations. So we get 0x, 0y, 0z. That's a 0 equals 0. From the second line, we get 0x, 2y plus 5z equals 0. Then the last line, we get 4y plus z equals 0. Okay, so maybe we can solve for x. No, we cannot solve for x because nothing helps us finding x. Let's leave it. So we don't know what x is. That's fine. Now, what about the y and z? So from the second equation and third equation, we can use substitution or elimination. So let's say we use substitution. So z equals negative 4y. If I put it into the second equation, so I get 2y plus 5 times negative 4y equals 0. So I have negative 18y equals 0. So you got y equals 0. If y equals 0, put it back in here, then z must also equal to 0. Okay, that's fine. So x we don't know, but y equals 0, z equals 0. That's okay. But remember that v has to be non-zero. So the eigenvector has to be non-zero. Okay, so what about x? We couldn't solve for it. That's fine. That just means that we're going to pick an x value. So pick a x value, because it could be any number. They're all going to be okay. So let's just say we pick x equals to 1 to make it easy. So we get 1, 0, 0. This will be my first eigenvector. So whenever there's some variable that you can't solve for it directly, just pick a value for it. If we can solve for it directly, even if there's 0, then we keep the 0 value. Like in this case, the y and the z. The 0. We cannot pick any value for y and z. They have to be 0, right? But the x we can pick. Any questions on this first eigenvector? Now I'm going to find the second eigenvector for lambda 2 equals 8. I'm going to do it a little bit quick. Is that okay? So a minus lambda I, that's going to equal to, you know what, I'm just going to be lazy. I apologize. So I'm going to write down the a minus lambda I times b equals 0 entirely. So that's going to be a minus lambda I. That's going to be 2 minus 8, 0, 0, 0, 4 minus 8, 5, 0, 4, 3 minus 8. And then that's going to multiply with v, x, y, z, which is equal to 0, 0, 0. Is that notation okay? Just me being a little bit lazy at this point. And from here, if we convert to system of equations, we get 2 minus 8, negative 6, 0, 0. So negative 6, 0, 0 times x, y, z. So we get negative 6x plus 0y plus 0z equals 0. And from the second line, I get 0x, 4 minus 8 is negative 4. So minus 4y plus 5z equals 0. And from the last line, I get 0x plus 4y, 3 minus 8 is negative 5, so negative 5z equals 0. So we end up system of equations here. And from here, we can solve for x in this step. So negative 6x equals 0, so x has to be 0. And then from the second line, we get negative 4y plus 5z equals 0. Not much we can do. We can divide by negative 4, but that's give us a fraction. So I'm going to leave it. So I'm going to write 4y equals 5z, or maybe 5z equals 4y to make it better. And the last equation gave me 4y equals 5z. It's the same thing as the second one. So there we have this 5z equals 4y. That's the only thing we know about y and the z. It's not enough to solve for y or solve for z. So that gives us a freedom to choose. So we can choose either the value for y or the value for z. It's up to you. You can choose any number as long as you feel like it's relatively easy for you. So in this case, I'm going to choose y equals 5. If I choose y equals 5 and solve for z, so that z will be 4. And x equals 0. So we have a vector v2, which is going to be 0, 5, 4. I could pick y equals 1, and then the z would be 4 over 5, but I don't like fractions there. So let's what I did. I avoid fractions. And then we can do the same thing for lambda 3 equals -1. So just be a little bit careful here. We plug in negative. So the a minus lambda I times v equals 0. So that becomes a minus lambda I. So 2 minus -1, 0, 0, 0, 4 minus -1, 5, 0, 4, 3 minus -1 times x, y, z equals 0. And if we convert it into system of equations, 2 minus -1 is 3. So 3x plus 0y plus 0z equals 0. And at the next line, I get 0x, 4 minus -1 is 5, plus 5y plus 5z equals 0. And then I get 0x plus 4y plus 4z equals 0. And we can solve for x, y, and z from here. So it turns out that x has to be 0 again, because we get 3x equals 0. And then we have 5y plus 5z equals 0. So we get y plus z equals 0. So we get y equals -z. And the same thing from the last one. That means this tells us that we can choose either z equals 1 or y equals 1. It doesn't matter. Or it could be anything else, right? So I'm going to choose y equals 1. Therefore, z will be -1. So here we have a vector v3, which is going to be 0, 1, -1. So that's how we find those eigenvectors and eigenvalues with the 3 by 3. Sometimes, the numbers are not nice. It might take a while, but the process is the same. I guess the only takeaway that I want to highlight is it's in the beginning, when we find the determinant of a minus lambda I, we found this, try to factor that instead of like expanding everything fully, because if you do that, then you end up with the cubic expression. It's difficult to factor. So if you can factor easily from the beginning, just try to factor as much as you can instead of try to expand fully. Any questions about this example? And I kind of went through a bit too fast. I apologize for that. All right, if you don't have any questions, I'm going to move on to my next example, which is solving system of equations. So example 2. So using eigenvalues to solve method to solve system of linear ODEs. So suppose we are given this example, x prime equals -5x plus y, y prime equals 4x minus 2y. So in this system, x prime is really just dx dt, and the y prime is dy dt. So basically what we have is x is a function of t, and the y is also a function of t, but the derivative of x depends on x and y, the derivative of y depends on x and y, right? So we're looking for a solution. So the solution at the end we look for is going to be x of t equals something, and y of t equals something. That's one way to think about it. Another way to put the solution is we can say, okay, this is a capital X of t is equal to x of t, y of t, and what is that equal to? Right, so that's what we want to find. But to solve that, we can use the eigenvalue method, which first step we have to do is we have to convert this a matrix equation. So that's a kind of the preparation work we have to do. So how do we convert to a matrix equation? The left-hand side, we're just going to kind of put the derivative on the outside. So that's going to be x, y. It's really x of t, y of t, x, y prime. That's going to equal to the right-hand side. We're just going to pull out the coefficients, put the coefficients into a matrix. So -5, 1, 4, -2. And then the remaining part is x, y, which is x of t, y of t. You don't have to write the t there, but just want to show you what they are. So that's the very first step. So we basically convert the system into this kind of a x prime equals a times x problem, a being the coefficient matrix. And how do we find the solution? Well, if you can put into this form, and a being the coefficient matrix, then the solution already we know has a form of x of t, y of t. So the solution has the form of c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. This is something worth to remember as a solution of a linear ODE, where lambda 1, lambda 2 are eigenvalues of A, the coefficient matrix, and the v1, v2 are eigenvectors of A. So the bottom line is, if we know v1, v2, lambda 1, lambda 2, then we can find the solution because we just take them, put into this form. So this method really comes down to find out the coefficient matrix A and finding the eigens from there. So let me quickly do it. I know you probably feel confident with it already, but I just want to, do the work. I'm going to do it a bit quick if you're okay with it. If not, feel free to, let me know. I'll slow down. So A we know, which is so A is -5, 1, 4, -2. Well, we first need A minus lambda I. So that's going to be, I'm just going to subtract lambda from the diagonal entry. So -5 minus lambda, -2 minus lambda. The rest is the same. Right? And then we need to know the determinant of this. And this is a 2 by 2. So we're just going to use this backward slash minus the forward. So that will be -5 minus lambda, -2 minus lambda, minus 1 times 4. There's not much we can factor, so I'm going to expand it fully. When I expand this, I get 10 plus 5 lambda plus 2 lambda plus lambda squared minus 4. So we get lambda squared plus 7 lambda plus 6. We can factor this. That's going to be lambda plus 6, lambda plus 1. And then we set it equal to 0 at the very end to find eigenvalues. So set it equal to 0. So we get lambda 1 equals -6, lambda 2 equals -1. It doesn't matter which one is the first, which one is the second one. Right, so those are the eigenvalues. Okay, good. So we get the lambda values, but we have to find the eigenvectors corresponding to them, right? So that's the next step. So to find eigenvectors, let's see, for the first one, so for lambda 1 equals -6, and I'm going to use this a minus lambda I that we found earlier, just plug in -6 in there. So we get a minus lambda I, which is going to be -5. So let me write it down. So a minus lambda I is going to be -5 minus -6. So be careful when you subtract negative numbers. 1, 4, -2 minus -6, right? And then that's just going to be -5 plus 6. That's a 1, 1, 4, -2 plus 6, 4. And then I'm going to take this matrix, multiply by xy, set it equal to 0. So you get 1, 1, 4, 4 times this eigenvector. You can call it xy, but it's not the same xy as before because the xy were the functions. But here it's just some values. So that's supposed to be 0, 0. And then we can figure out this is going to be x plus y equals 0, 4x plus y equals 4y. Sorry, equals 0. So it really is the same equation, just x equals -y. And then we have to choose value. So choose x equals 1 or 2, doesn't matter, it's up to you. So y equals -1. Therefore, we have v1 is equal to 1, -1. So that's the first eigen vector. And then we can do the same thing for the second one. So for lambda 2 is equal to -1. So I'm going to be a little bit lazy because I guess it doesn't matter. So a minus lambda I times v equals 0. So a minus lambda I is going to be -5 minus -1, 1, 4, -2 minus -1. So just be careful when you subtract negatives. It's very easy to kind of forget about a negative sign. Times x or y is equal to 0, 0. And that will give us -5 plus 1, -4x plus plus y. And then we have 4x minus y, both equal to 0. And then again, two equations, really just one equation is 4x equals y. We have to choose the x value. So choose x equals 1, so y equals 4. So we get this v2, which is 1, 4. Now we found lambda values and the eigenvectors. We can figure out the solution. So the solution is going to be capital X, or you can just, instead of writing capital X, you can write down x of t, y of t. So that's going to be equal to C1, V1. V1 is 1, -1, right? And then e to the lambda 1, you have to be careful. Don't mix the lambdas with the eigenvectors. So this is a V1 corresponding to lambda 1 equals -6. So they go together, e to the -6t. And then plus C2, V2. V2 is a 1, 4. And then e to the lambda 2, which is -1. So they go together, -t. So that's my solution in vector form, right? Now, from here, there's a couple of things we could do. We could find the scalar form, which is, so from here, we can find the scalar form, which is going to be x of t equals something, y of t equals something. To do that, there's a very short, sort of like an easy shortcut, or you can just take it formally. So the formula is take the C1, distribute into the vector, e to the -6t put into the vector, C2 put in there, same thing, e to the -t. And then we add them. Now the shortcut is kind of just read the top line and read the bottom line. the top line will be x of t, c1, 1, e to the negative 6t, c2, 1, e to the negative t. So put that together, that will give us x of t, which is c1 times 1, e to the negative 6t, plus c2 times 1, I'm not going to write the 1, and then e to the minus t. So that's x of t. Then the y of t, it's going to be y of t, c1, negative 1, e to the negative 6t, c2, 4, e to the negative t. So y of t is negative c1, e to the negative 6t, and then plus 4, c2, e to the negative t. So this is the scalar form. All right, I should stop because I feel like I'm rushing through this material. How are you guys doing? I do apologize for going through a bit too fast towards the end, but let me pause and for you to ask questions. Okay, I'm not hearing any questions. What does it, okay, can anyone just tell me, please, does this kind of make sense, what I did so far? Were you able to kind of follow through?
Yeah, I was able to follow through. I was just still wondering, say for some arbitrary reason, like you had a initial value problem,
Yep,
like x of 0 equals something, would you just plug in 0 for t and then solve it that way?
exactly. That's what I'm going to do next. Yeah.
Okay, awesome.
So when you're solving for the x of t equation, you're just multiplying everything that's on the top. And then when you're finding the y of t, you're doing everything on the bottom.
Exactly. Yep. Just also keep the, keep the coefficient and also the exponential part with those numbers. Exactly.
Okay, but for y of t, why is it minus 6 at the end?
Ah, thank you. I just want to make sure you pay attention. So that's a minus t. Thank you.
Okay,
catch.
now it makes sense. All right, I was confused there. Okay.
Yep. Good, very good catch there. It was my fault. All right, so that's a general solution. Now, if we want to know C1, C2, we have to have some initial condition. So in this beginning, I didn't give you initial condition, right? So let's just say we finish solving this problem to this point. Suppose at the beginning, we're given some initial condition. Let's see, x of 0 equals 0, y of 0 equals -4, for example. And those are initial conditions given in at the very beginning. We solve for the specific solution. So we do pretty much the same work we have done before. And now we're just going to use this initial condition to figure out C1, C2, and find the specific solution. So it doesn't matter which one you plug in. Each of this is, this one says t equals 0, x equals 0. This one says t equals 0, y equals -4. So you can plug into this vector form, which I'm going to use because it's a little bit easier, I think, but it doesn't matter. Or you can plug in here. It doesn't really matter that much. But let me practice with a vector form. So if I put in t equals 0, so all the exponential parts become e to the 0, that's a 1. But the x of t on the left, so that's going to be 0. And the y of t is going to be -4. And that's equal to c1, 1, -1, e to the -6 times 0, that's good, plus c2, 1, 4, e to the negative times 0, well, e to the -0. The exponentials with a 0 in the exponent is going to be 1. So we just have 0, -4 equals c1, 1, -1, plus c2, 1, 4. And from here, you can convert it into system of equations, just like we had earlier on top. So that will be 0 equals C1 times the 1 plus C2 times the 1. And then we have -4 equals C1 times -1 plus C2 times 4. And this is the system of, two equations, two variables, right? We can solve them. It's up to you which one to solve it first and which method to use. You can use elimination, substitution, or matrix equation, whichever you feel comfortable at this point. So if you use elimination, you can add them together. Equation 1 plus 2 will get rid of the C1s because the 1 is positive, 1 is negative. So that gives us -4 equals 5 C2. So C2 equals -4/5. And then how do we solve for C1? I use the first equation because I have a 0 on one side. So from the first equation, we get 0 equals C1 plus C2. So C1 equals -C2. Therefore, C1 equals 4/5. And if we know C1, C2, then we can figure out the solution. So that's going to be capital X of t, or you can write as X of t, Y of t. That's going to be equal to C1, 4/5, V1, which is a 1, -1, e to the -6t, and then plus C2, which is -4/5, 1, 4, e to the -t. So just take C1, C2, put back in there. So that will be the specific solution. You have to have initial condition in order to solve for C1, C2. If you don't have them, then we can't really solve it. We have to use something else, some other information given. Like for example, when t equals 5, the x value, the y value. Questions on what I did there? You don't have to plug in here. If you plug into the scalar form that we already have x of t equals something, right? Y of t equals something. We plug in t for all the t's and plug in the value for x and y. We should end up with the same system of equations with C1 and C2. Then we solve for them, then we can use them back into this scalar form. All right, questions? If you don't have questions, I believe we can finish early today, which haven't really happened that frequently. Like I said before, this will be recorded and posted on the internet. The link is the same link in the announcement. So if you kind of want to go back and look at it again, feel free to do that at any time after tonight, I think. And when you do homework problems, I think you should be ready because I don't think there's anything else in the homework that I have not talked about or Professor Gibson have not talked about. So you should be okay with the homework. If you have any questions, again, feel free to let me know or email Professor Gibson, and then we can help you out. All right, so I'll stick around for a few minutes just in case if you have questions. Other than that, I'll see you on Tuesday. Have a great weekend, everyone. Take care. All right, thank you.